All right, hi everyone. So today we're going to talk about how to design an experiment. We talked about the scientific method. We talked about what those different steps are to go through and solve a problem. And one of those steps was the testing phase, right? So that's what this lesson is all about. It's about how do we design the actual test. And we can design lots of different tests, but what we want to do here is design a valid test. So that's the key here. How can we design a valid test? And we have to make sure we understand the different parts of the test to make sure that it is valid for us. So we're going to start with the terms, and we're going to describe what those terms are, define what those terms are, and then we'll go through an example at the end. Okay? So what are the terms that deal with these, with this experiment phase or this testing phase? Obviously, we have the experiment itself. We have what a hypothesis is. We sort of went over that a little bit before. We have the dependent variable and the constant, the independent variable, and then the controlled variable. So we got all these terms we have to understand before we can put it all together to make a valid experiment. So what is that experiment? So the experiment is, and this is the key word here, an organized procedure for testing a hypothesis. So the main thing to point out here is that it's organized. It's not just a random, just let's try this, and it's not trial and error. That is not an experiment. An experiment has a purposely thought out, step-by-step plan to make sure that we don't mess up. Okay, so that's why typically when we write an experiment, when we draw up our experiment, we have to write our procedures first. We want to know what those steps are, so that we're following a plan, we're following steps. We're not just trying something and hoping it works out, because we want to be able to repeat this experiment. So if we don't have a set of steps, we won't be able to do it exactly the same way. Okay, so it's a process in which you test to see how one thing affects another. So this is the type of investigation. This is not an observational investigation, but this is a conditional experiment, a conditional observation. So what's the hypothesis then? Again, we already stated this one before, so this should be a review here. The hypothesis is a proposed solution for the problem based on what you already know or what's been observed. So again, based on the background research that you have, you can come up with an idea, come up with a possible solution to that problem. Okay, so that's what a hypothesis is. Now, when we write our hypothesis, we want to write it in a very specific way. So a hypothesis has to be supported with logical thinking. So that means that we have to support our hypothesis with our background information. We can't just randomly come up with an idea. You could, but that's not a hypothesis, that's a guess. A hypothesis is not a guess. We're not guessing. We've done our research, we've done our background search on the internet, in the library, in books, whatever. We've looked up that information, and now based on that information, we have an idea of what the solution could be. That's what a hypothesis is. It has to be supported by logical thinking. So a good hypothesis, an easy way to start writing hypotheses, they don't always have to be this way, but a good way, and the way that we're going to do it this year, is we're going to write our hypothesis as an if, then, because statement. And I'll show you an example of that down the road. But every hypothesis we have has to have an if we do this, then this is going to happen, because based on our research, this is what the research tells us should happen. So if, then, because, the three parts of the hypothesis. So what's an independent variable? An independent variable then is the factor or the variable, that's what a factor is, a variable, or the part of the experiment that is changed on purpose. So we're going to change something on purpose. This is, if you remember our last lesson, there was two groups of students taking a test, right? And one group of students was taking a test in a nice quiet room, and then the next room had a band playing in the background. So what was changed between those two rooms? The same test, the same desk, everything was the same, but the only thing that was different there was the sound of the room, the noise level of the room. So that would be the variable that we changed. We did that on purpose. Why? Because we wanted to test to see, does that impact the results? So an independent variable is the factor in an experiment that is changed on purpose to see how it affects something else. So it's what we're changing. Now, again, as we get to do this more and more, some people have a hard time figuring out what the independent variable is. And there's an easy way to sort of associate this with you. If you put yourself in the place of the experimenter, so maybe you're looking at somebody else's experiment, maybe you're doing your experiment yourself, whatever. Ask yourself this, since independent variable starts with the letter I, right? Ask yourself, what am I changing? The independent variable is the factor that I changed on purpose to test. All right, what did we change? What did we what did we do? So in the example with the test, the students, what did we change? We changed the noise level of the room. Okay, so the independent variable is what the experimenter has changed on purpose in order to test to see if it has an effect. We talk about levels. So this might be new to a lot of you, but you've been doing levels, you may not have called it levels. So what's a level of an independent variable? The level of the independent variable simply describes the number of different changes that you're going to try. So in our example, again, with the noise level, with the music in the classroom, right? Maybe we do that and we have 5 different classrooms, and we have each are taking the exact same test, each have the same environment, each has the same temperature, everything's the same, but each classroom, the noise level is a little bit different. Maybe in the first one there's no noise. The second one there's just a flute in the background playing. In the third one there's a flute and a drummer playing in there. And then the last one there's a whole marching band in there. So what did we change? We changed the levels of noise. We're still changing the noise, but we're changing different levels of it. We're starting with no noise, then a little noise, and a little bit more noise, then a lot of noise, right? So those are the different levels. Each of them is still the independent variable because they're all still dealing with the noise level of the classroom. So every experiment has to have a minimum of 2 levels. Every experiment. So you've been doing levels, you just haven't maybe called them a level. The very first level is what we call our controlled level. Okay, so it's the level that we're going to compare everything to. We'll get to that in a second. The second level and beyond are everything you're changing. So again, in our classroom of noise, our controlled level would be that first level where there's no noise. Then the second level would be the flute, and the third level would be the flute and the drum, and so forth, until we get to all of our different levels. In this picture here you're looking at, she has 3 containers. One's marked control, one's marked A, one's marked B. Maybe she's trying to figure out how to make the best lemonade, and so she has one thing that's maybe she's changing the amount of sugar in the water, and maybe in the control there's only 1 scoop of sugar. In A there's 5 scoops of sugar. In B there's 10 scoops of sugar. Maybe that's her experiment. I don't know, just based on the picture. But there's 3 containers there. So in other words, she has 3 levels of her experiment. She's changed something 3 different times. Okay? All right, so what's the controlled level? The controlled level is that first level, and it's the level of the experiment that does not introduce change. So the easiest way to say this is that the controlled level is what we always consider to be normal. So again, in the taking a test example that I've been using, the normal way you take a test is without music blasting in the background, without a marching band standing behind you, right? So that would be our controlled level. In the lemonade example, maybe you always put, most lemonades, you put 1 scoop of sugar in it. That's the normal way that you do it, not 10 scoops, not 5 scoops, but 1 scoop. So it's always what is typical, what is normal. All right. Once you have that normal established and you make that your controlled level, this is what normally happens, right? Then all the other data from all the other levels are always compared to that, because we're trying to impact the change. So if we're trying to have the best lemonade, the best tasting lemonade, or the sweetest, maybe the sweetest lemonade, you would have take a sip of the controlled, which has 1 scoop, and then take a sip of the 5 sugar, then a sip of the 10 sugar, and compare it back to the first one. Is this sweeter than that? Is that sweeter than this? With the music, does the noise level make the test scores go down? So we're going to look at the test scores and see if with greater volumes, did the test scores go down? But how do we know where the test scores should have been? We have to go back to that first level where there was no music and say, this is the normal way people take a test. If you have a flute, does it make the test scores drop a little bit? If you have a band, does it make it drop a lot compared to that first level? So the controlled level is typically mixed up with another word that's in our experiment, and that's typically mixed up with constants, which we'll get to in a second. The dependent variable, what's our dependent variable? Our dependent variable is the factor in the experiment that we expect to change. So based on what we're changing with the independent variable, we expect this to happen. Okay, so what was our expected change in the music? We changed the noise level, we increased the noise level, and what did we expect to happen? We expected the test scores to go down. So changing the noise level was our independent variable. Our test scores dropping was our dependent variable. That's what we're testing to see. Does noise level impact or change the test scores? So the thing about the dependent variable is we have to be very specific with that. It has to be something that we can measure. So when you're collecting your data, this is your dependent variable. Your data that you're collecting is your dependent variable. So it has to be something we can measure, whether it's length or temperature or volume or whatever. But it has to be quantitative data for sure. All right, so again, constants. People mix up constants with controlled level all the time. The controlled level is the entire experiment that's normal. So this is the normal situation in the experiment that you're doing. What's a constant? So again, controlled level is the one normal thing. So the classroom with no noise. So it's the independent variable that's normal. Okay? What's a constant? A constant is all the factors in all the levels. So if you have 500 levels, all these factors that are the same in every single level. In other words, we don't want to change anything but one thing. That's the independent variable. So constants are the factors in every level of the experiment that do not change from one level to the next. So let's think about the music and the test. What would be the same about each of those classrooms? Yes, we changed the noise level, right? What would be the same in each of those classrooms? The test should be the same. The room temperature should be the same. The type of desk that they're sitting in should be the same. The type of pencil should be the same, right? So all those things are the same. Those are all constant. That every room is going to have those exact same things, no matter what the noise level is. The only thing that should be different between those levels is the one variable that you, the experimenter, is changing, the independent variable. Okay? If you change more than one thing, there's no way to know whether or not your independent variable truly impacted your dependent variable or not. So we have to only change one thing and nothing else. If we would have, let's say this, in that noise, in the classroom noise, right? So let's say the first test was an AP physics test. AP physics test, no noise. Level 5, the one with the whole band behind you, right, was a kindergarten spelling test. So you had words like cat, dog, the, right? What might we see in that case? We might see that people got better test scores. But can we prove then, does that then say that having a louder environment will make you have a better test score? No, because what did we change? We changed the noise level and we changed the test. We changed two variables. You can't do that. one thing changes, the independent variable, and everything else has to stay exactly the same between all the levels. Okay? So, if you change more than one thing, there's no way to tell what factor actually caused the change. Was it the music? Could be. Was it the easier test? That could be. Was it a combination with them? Might be that too. You have no idea. If you only changed one thing, then you would know whether or not it had an impact. If it didn't have an impact, then what do? Then you take your independent variable, you leave that now, that becomes a constant, and you take one of your constants and it becomes a new independent variable. In other words, when you go back and retry or remake a hypothesis, you're switching the independent variable in one of your constants and you're trying something new to see if that has an impact. But your constants have to be the same for every single level. Okay? Only change one at a time. How many trials? We talked about this before, right? A minimum of 3 trials. So by repeating an experiment more than once for each level of the experiment and getting similar results each time will make the data reliable and valid. We talked about that before, about the fact that if we get the same results over and over again, it starts to validate that that data actually is true, and it takes away a bias as well, right? So we want to make sure that we eliminate bias by doing these several trials. If you have several trials that are all similar, which numbers do you actually use? Well, the best way to do this is to, take your quantitative data, that's all your numbers, and find the average of all those. Okay, find the average value of all your data. And finding the average will eliminate maybe some small human errors that you made in your data collection. Maybe when you were recording temperature, you were supposed to record it every minute, and 1 or 2 times you let it go 5 seconds over that minute mark before you read the thermometer. And so that's not exactly a minute though, right? So that's a little bit of an error. Maybe you're using a stopwatch to time something as it's rolling down a ramp, and when you hit the bottom of the ramp, you're supposed to stop the stopwatch, but you missed it by like a few milliseconds. That's not perfect either. By finding the average of all these numbers, it helps eliminate those little possible errors that you might have had. Now, if there's big numbers, big differences, those are called outliers, and we want to just sort of take those far ones on the top and the far ones at the bottom, just get rid of those, and just concentrate with the ones that are near each other. Okay. All right. After you're done with your experiment, this is where you sort of draw your conclusion, and it's with your C.E.Rs. Hopefully your teachers in the past have talked to you about C.E.Rs. What does the C.E.R. stand for? The C stands for claim. This is where you're going to make a statement about an argument. Basically, you're going to restate your hypothesis and say, this is what I believe to be true. Okay? So your hypothesis, if it was correct, you're going to say that, you're going to restate your hypothesis and say that this is what I believe to be true. If your hypothesis was wrong, you're going to restate your hypothesis and say, this is not true, whatever. But you're going to restate that as a claim. This is, based on what I just did, this is what I believe to be true. The E stands for evidence. You're then going to tie your evidence from your experiment to your claim, saying this evidence backs up my claim. Specific numbers from your experiment. And then the R is the reasoning. This is your scientific rule, or this is the science behind your evidence. Why does your evidence, or how does your evidence support your claim? So, claim, this is what I think to be true. Evidence, this is what tells me that my claim is true. And reasoning, this is the scientific facts, or the scientific rules that tells me that the evidence that I chose is the right evidence to support my claim. So we'll work on that, but this is our C.E.Rs, and you are going to be doing this throughout the year if you haven't already been doing it in the years past. Okay? All right, let's look at an example here. Here's an example of an experiment, and we'll go through the whole thing, and we'll try to come up with and identify all the different parts of this valid experiment. So here we have a professional soccer player. If anybody doesn't know who that is, that's Alex Morgan. So Alex Morgan has and plays soccer for a long time. And maybe she's sitting on the field and she is observant. She's wondering about things. And that's how science starts, with that wonder, with that questioning. And she says, hey, I wonder how air pressure of the soccer ball affects how it's kicked. So how does the air pressure of a soccer ball affect the distance that it can be kicked? So that's a legitimate question. Soccer balls are supposed to have so much air in it. If you put too much air, if you have not enough air, is that going to impact the distance that it can be kicked? And how so? How will it affect it? So she sets up an experiment. The first step after she identified the problem is to do some background research. So she gets out her physical science books. She gets out some websites and she starts looking at stuff and researching about how air pressure works and how a soccer ball is kicked and all sorts of stuff, right? And after she's done with that research, she believes she has an answer to her question. And she states her hypothesis like this. Remember, we're looking for the if, then, because statement. So she says, if a soccer ball's air pressure is increased, then the kicked distance of the ball will also increase. So notice we have the if and then statement there. So if the air pressure is increased, that's the if, then the kick distance will also increase. So we're talking about two different variables. The if variable is air pressure, the then variable is kicked distance, and we're also describing what's going to happen. If we increase the air pressure, then the kick distance will also increase. That's what her hypothesis says. We're missing something though. We're missing the because. So she continues her hypothesis with the because. So if a soccer ball's air pressure is increased, then the kick distance of the ball will also increase because my research shows, or her research shows, that more air will cause a soft object to become more firm, which increases the effect of Newton's third law. Now, you don't have to know what that law is right now, but what's that because statement show you? It shows you that her idea, this if and then, this hypothesis, is not just some random thing she's going to try or some random thing she believes. It's based on some of her research. So she must have researched something with Newton's laws. She researched stuff with air pressure and found out that more air pressure increases pressure. So, or more air inside of a ball increases the pressure, so it becomes more firm, more solid. So that's all stuff that she's basing on. Whether it's right or wrong, we don't know yet. We have to figure that out with the test. But the thing is, she has a hypothesis. Now, if you write your hypothesis this way with an if, then, because statement, you've already identified two of your parts of your experiment. The independent variable of her experiment is the if statement. So what variable is the if? It's the air pressure, the ball's air pressure. She's saying if I, remember what the independent variable is, what the person changes. If I change the air pressure of the ball, so what is she changing? She's changing the air pressure of the ball. The dependent variable is what she hopes will happen after she changes the air pressure of the ball. So that's the then part of the hypothesis. What is she hoping will change? She's hoping that the kicked distance, or the distance that the ball is kicked, will change. So our two variables here, our independent variable is the air pressure in the ball, and our dependent variable, what we hope to change, is the distance that the ball is kicked. Your hypothesis gives you your independent and your dependent variables. All right, what are some levels? Well, let's say that she does some research and she says, we need our first level to always be our controlled level. So what should that controlled level be? Remember, the controlled level should be the one that's most normal. So, according to World Cup, the official PSI of World Cup soccer balls is 8.7 PSI. Now, they don't really use PSI, they use pascals, which is different measurement, but it's, since you're more familiar with PSI, we'll do PSI. So 8.7 PSI. So that's her normal. That's the official pressure of every soccer ball that she plays with, Major League Soccer. So that's level 1. Is that an experiment? Nope. We got to have a minimum of 2 levels. So now she says, all right, let's change. What was she changing again? She was changing the air pressure. So second ball, she adds a little bit more air. So instead of being 8.7, she goes up to 9 psi. So it's a little bit more air pressure. So now she has 2 levels. This is an experiment. She could be done right here. But she decides to do a couple more. So she does a 3rd level where she does, if she went slightly higher with the 2nd level, she went slightly lower with the 3rd level, so only up to 8. And then she decided to go extremely high, so she blew it up to almost the point where the ball was going to explode. And she's at 15 psi. So she figured if she went extremely high, she might as well go extremely low. And so the lowest one was 2.4 psi. The picture here is probably not true. It probably would still be a spherical shape, just not quite like that. Maybe that's after she kicks it. Anyways, so how many levels does she have? She has 5 levels. Each level, what did she change? She only changed the psi. She only changed the air pressure. Which level was her controlled level? It's the one that was most normal, the official psi. So now she has to come up with, now she has her independent variable, her dependent variable. She's identified her levels. She's identified her controlled level. What she have to do now? In order to make sure this is a valid experiment, this is the hardest part, she has to keep everything else constant. Everything else has to be the same. So she decides to take her test to an indoor facility and do her kicking test there. Why would that be better? What's going to be the same at an indoor facility? Well, the weather's going to be the same, right? So you're not going to have rain for one kick and no rain for another, and hot and cold. It's going to be the same conditions are going to be there, right? It's not going to be windy one kick and not windy another kick. The field is the same. So everything there, the turf, how it bounces, it's all the same type of material. So that's a good thing for her to do. She probably also should not kick the ball herself. Why? Well, if you've ever kicked a ball or thrown something, whatever, do you throw it exactly the same every single time? Do you kick a soccer ball the same every single time? No. Even if you were the most talented athlete in the world, you couldn't control your kick so it was exactly the same amount of force every single time. So one of the things maybe she looks up on the internet or on YouTube or something like that, and finds that, and this is a video you can actually find, that these kids here built a soccer kicking device. It basically just works on gravity. It's a pendulum where you pull the weight back to a certain spot, you release it, and it kicks the ball always with the same force, because it's the same weight falling the same way every single time. So that means that the kick has the same force for every ball. So if we follow all these constants and do all these things the same, that means that the only thing that should be different should be the air pressure inside the ball. Again, the constants are where most people mess up. If you change a constant, you're changing 2 variables, and now we have no way of knowing whether or not it truly was your independent variable or not. So let's assume that she did everything else the same, okay? And then let's look at the data that she collected. So the data that she collected is right here. You'll see that, what did she do? She did 3 trials, right? So she has distances for trial 1, distances for trial 2, distances for trial 3, and then she averaged them all together. Does this prove or disprove her hypothesis? That's for her to decide. We already mentioned this before, but which level represents her control? It's that first level, right? So that first level, notice the average for the official PSI with our kicking device was 5 meters. What she wants to know is, what? By increasing the air pressure, will it increase the distance kicked? So go down to 9 PSI. Did it increase the distance? Well, we increased the air pressure and the average distance went from 5 to 5.7. I'm always going to go back to level 1 to compare. 15 PSI. So now we go 15 PSI. That's much higher than the first one. So we went from 5 to 6 meters. So it's still increased, but not linearly, meaning it's not the same. It should be much higher if it was a linear change. So that's a different question. But again, that's the whole point of science, is that one question leads to many other questions here. So that's, in a nutshell, how to design an experiment. So we have to know what our independent variable, what our dependent variable is, what our controlled level is, what our constants are, okay? We have to understand all those and how to write a good hypothesis, an if, then, because statement. If you understand that and we start applying that to our own experiments, you're going to end up having more and more valid experiments. If you mess this part up, whether you have a really good plan or not, your entire experiment, your entire investigation could be jeopardized because you didn't experiment correctly. So only change one level, that's your independent variable, keep everything else constant, okay? And then always compare it to your controlled level. Hopefully you found this helpful, and we'll talk to you later. This week we'll get into some more examples of some experiments, but otherwise, see ya.